right, thanks Dr. Tetro, and thanks Desmond for getting us set up on his laptop. All right, I'm Will Monroe.
And I'm Angel Chan.
And this is joint work with Manolis Sava and our advisors, Christopher Potts and Christopher Manning at Stanford University. And so I'd like to start by giving a bit of background and motivation for this task before I go into the details of our contribution. So 3D scenes are used in a wide variety of creative applications. Probably the most famous ones that you'd be familiar with are 3D games and animated films. But 3D scenes are also used by interior designers, architects, product designers in order to visualize what their product will look like before they actually create it. And many of these 3D scenes don't start their lives as 3D geometric representations or even as visual sketches, but they actually start their lives as natural language. So here's an example of a screenplay that lays out this scene from Disney's Pixar 3, from Disney and Pixar's Toy Story 3. It starts out an idyllic daycare classroom filled with the happy bustle of 4- and 5-year-olds playing with toys. And from this description, a large team of designers and artists at Pixar had to painstakingly place every little object and detail in this scene in order to bring it to life. And a system for automatically generating 3D scenes from text has to play the role of the design team in this process. Now, clearly, there are a number of challenges associated with this, and there's been some work over the years in addressing these challenges. Probably the earliest example that we know of is Sherdloo by Terry Winograd in the 1970s, which demonstrated natural language understanding and moving blocks around in a 3D block world. More recently, probably the most notable work in this field is Word's Eye, which is especially important for using a realistically large database of 3D models in order to be able to generate a wide variety of scenes from text. The work that forms the foundation for our work that we're presenting today is a system developed by my co-author Angel and presented at EMNLP 2014. And the pipeline that's used in this system first starts out by parsing a natural language description to visual concepts, selecting concrete objects to realize those concepts, and then laying out these objects respecting the constraints in the description in order to create a completed scene. Now, the main problem that we hope to address with this work is the problem of lexical variety. The problem here is that any given object can be described using a wide variety of terms. And so, for example, this piece of furniture on the bottom here for storing clothes could be variously described as a dresser, a chest of drawers, a cabinet, cupboards, bureau, et cetera, et cetera. All of the systems that I've mentioned so far use manually constructed mappings in order to try to ensure that all of these terms are going to be interpreted correctly and realized as an object, something like this. A problem that's related to this is the problem of handling unexpected descriptive terms. So this is an example from our previous system where the parsing stage of the system did not realize that the word wood was supposed to be a modifier for the chairs and dutifully inserted 4 of them, 4 woods, as well as some chairs. Now, what we hope to do with this work is to fix problems like this by learning from data. And so, our contribution has 4 main parts. First of all, we introduce a new data set that consists of 3D scenes as well as their descriptions. We introduce a method for extracting lexical knowledge from this data set. We combine this lexical knowledge with a rule-based parsing system, and then we present a quantitative evaluation that shows that this combined system outperforms both previous rule-based systems as well as a system using only the lexical knowledge alone. So I'll start by describing the data set. We collected this data set using Amazon Mechanical Turk. The way we collected it is we started by writing out a set of 60 seed descriptions, as we call them, that contain very simple language that just specifies a small number of objects that should be present in the scene. So for example, there is a bed and there is a chair next to the bed. And we gave each one of these seed descriptions to a number of Mechanical Turk workers and asked them to design a scene to match the description using a simplified online interface. Here's a picture of this interface, this is to try to show the structure of the 3D scenes that they're building with this system. Each 3D scene consists of some number of 3D models, each of which is identified by an ID, as well as their spatial transforms. You can think of this as position, scaling, and rotation. And then each 3D model is linked to a database that gives you exactly what model it is, what it looks like, as well as some human-curated information about what the object is. So we have some keywords that are labeled, a category for the object, a link to a lemma in WordNet, as well as some geometric parameters that tell you by default how big should the object be and what is its front and top. So once we have these scenes designed by Mechanical Turk workers, we give the same scenes to a different group of Turkers in order to obtain more varied descriptions of these. So we don't want each scene to be associated only with the seed sentence. We want real natural language in order to describe these scenes. You can see that not only is there a lot of variety in the scenes that are produced, so these 3 scenes are all from the same seed sentence, but also you see a lot of variety in the descriptions that we get in the final step. So everything from the minimalist, I see a bed and a chair, to much more elaborate descriptions, something that might come straight out of a home design manual, like floor-to-ceiling windows on the back wall, lights recessed into the right side wall, light wood flooring, so on and so on. So our completed data set includes these 60 seed sentences with over 1,000 scenes that were created from those, and then 4,000 descriptions. So every seed sentence yields several scenes, and every scene is described by several Turker-provided descriptions. Okay. So now that we have this data set, we can proceed to learn some lexical knowledge from it. And the way we do this is by setting up a scene discrimination task. So for each pair of Turker-designed scene and Turker-provided description of that scene, we create an instance that looked like this that contains the description, the original scene that inspired it, as well as 4 other distractor scenes that are chosen at random from the data set. And so if you look at this example, you can see that the only room that is accurately described as a brown room with a refrigerator in the back corner is scene D. So we train a classifier to perform this task of scene discrimination. We use a one versus all logistic regression model where our features are simple cross products of unigram and bigram features from the description and of individual model IDs and the human tagged category of each model on the scene side. And so while I should mention that doing well at this task is not the main goal of this work, we do notice a substantial improvement in accuracy at scene discrimination when adding in the human tagged categories, that this gives us quite a bit more power to generalize. So here's some examples of lexical grounding that we learn using this classifier. So these are just the highest weighted pairs of words and categories that we learn using this classifier. And so you can see that we do learn, as expected, some simple identity mappings, like chair goes to the category named chair, couch goes to the category named couch. But we also are able to capture a few lexical variations. So we notice that the word sofa is often used to describe the category that's called couch, and that the word bookshelf is used to describe the category that's called bookcase. Now you'll also notice that because our system doesn't actually have any compositional knowledge of scenes, that we do end up with a few false positives. Like for example, in our data set, fruit almost always occurs in bowls, and so we learn the errant mapping from fruit to the category bowl. And here are some more examples of specific model IDs that are captured using the high weights in this system. So you can see that there are some colors and shapes, as well as it notices that the phrase open window can be used to describe this last room, which has an open window in the back.